Now let's look at a concept known as bond polarity. And anytime we see the word polarity in chemistry, we are talking about the separation of a charge. When we are talking about covalent bonds between unlike atoms, atoms of different elements, many times that's going to result in unequal sharing of the electron. One atom is going to pull the electrons that are used in bonding closer to its side. And so therefore one end of the bond has more electron density than the other. So we have a separation of charge since electrons have charges, and this is known as bond polarity. So here's an example. Here we have hydrogen chloride, and here are the two electrons involved in the bond. Chlorine has a much larger nuclear charge than hydrogen does. And so the electrons that are being shared between these two atoms are being shared unequally. These electrons spend more time on the side of chlorine than they do of hydrogen. And so we have a partial negative charge on this side of the bond and a partial positive. The partial negative results because electrons spend more time over here and electrons have a negative charge. We use this lowercase Greek letter delta to indicate partial. We don't have a full charge here. Full charges come as the result of gaining or losing electrons. We just have a partial charge here due to an unequal distribution. We quantify this ability to pull electrons in a bond by the term electronegativity. Electronegativity is a measure of the pull an atom has on bonding electrons. Now, one very important issue here is it deals with bonding electrons, so electronegativity only has meaning in a molecule. The trend for electronegativity is opposite that of metallic character, and it follows the trend for it's opposite metallic character, and it's actually opposite size. The smaller the size, the higher the electronegativity. The higher the metallic character, the lower the electronegativity. So let's look at this little periodic table here. It has actual values for electronegativity, and we see as we go from left to right, our electronegativity values increase, and as we go up they increase. We also want to remember that this is the trend for small size. So as we go from left to right, the size gets smaller, and as we go up, the size gets smaller. Now, we're ignoring the noble gases here because electronegativity is only valid when we're looking at bonding electrons, and the noble gases typically do not bond. So we're only going to care about the elements that actually form compounds. So looking at our trend, our most electronegative elements are going to be up in this corner, and fluorine is going to be the most electronegative element on the periodic table. And down here, where we have the most metallic elements, these elements are going to have the lowest electronegativity. So the larger indifference between electronegativity of two atoms, the more polar the bond. And the negative end is going to be towards the more electronegative atom. So here we have hydrogen and fluorine. Hydrogen, all the way on this side of the periodic table, fluorine, the most electronegative element. There's going to be a big difference in electronegativity here, and the more electronegative element has the partial negative charge. You may see in your textbook and in other textbooks this color-coded electron distribution. Where it is negative, where it is red, we have larger probability of finding an electron, and where it is blue, we have a lower probability of finding an electron. So here we have this molecule, more electron density over here, near the more electronegative atom. Now there is a continuum between purely covalent, equally shared electrons, and then ionic compounds, where electrons really aren't shared, they're transferred. And we can use electronegativity to help quantify this continuum. If the difference in electronegativity between two bonded atoms is between 0 and 0.3, then the bond is considered to be pure covalent and non-polar, no separation of charge. If the difference in electronegativity between the bonded atoms is between 0.4 and 1.9, then it's polar covalent. So this is a polar bond. And then if the difference in electronegativity is greater than 2, then we consider it to be ionic. There's really not a lot of sharing going on. The non-metal is going to have the negative charge, and the metal is going to have the positive charge. So here are some examples. Here we have the pure covalent or non-polar bond. This is going to occur anytime two atoms of the same element bond. Since they both have the same electronegativity, the difference between them is going to be 0, and these are going to attract the bonding electrons to the same extent and share the bonding electrons equally. Here we have a polar covalent bond, fluorine, very electronegative, hydrogen, not so electronegative. We have a difference here of almost 2, which would make it ionic, so very polar covalent bond. And here we have an ionic bond. If we look at the difference in electronegativity between chlorine and sodium, we get 2.1, which puts it in the ionic realm. So here's our continuum, and here's our separation for the nonpolar, polar, and then ionic. Now, dipole moments is a measure of the separation of charge in a molecule. A dipole moment can be symbolized by this little arrow here. The positive sign indicates the positive part of the molecule, and the arrow points to where the electrons are going. So here's our little delta positive, delta negative, partial positive, partial negative. You can also use the arrow to show this. Polar molecules are going to have one end that is slightly positive, one end that is slightly negative. Now, these are not going to be full charges, they're partial charges, but they come from our asymmetrical or non-symmetrical electron distribution. Oxygen is more electronegative than hydrogen. It's going to pull the electrons used to bond these two atoms together closer to itself. The dipole moment is symbolized by this Greek letter mu, as in the sound that cats make, and it's a measure of the size of polarity. It's measured in dBs, symbolized by a capital letter D. Okay, so using your electronegativity values, determine which of the following bonds is ionic or covalent, and if it is covalent, indicate that whether it's pure, which would be non-polar, or if it's polar. And if it is polar, indicate the direction of the dipole, meaning which side is negative and which side is positive. So if we look at the difference in electronegativity between oxygen and lead, we're going to take the smaller from the larger. We get 1.6. So this would be considered to be polar covalent, and the direction of the dipole is going to be towards the more electronegative atom, oxygen. If we look at phosphorus and sulfur, which are close to one another on the periodic table, and we subtract their two electronegativities, we get 0.4, which means pure covalent or nonpolar. Here we have magnesium and chlorine far apart from one another on the periodic table. When we subtract the electronegativity of magnesium from that of chlorine, we get 1.8, which it says here ionic. That's not quite 2, so it really would be in the polar covalent region. And then here we have, and then if it is saying it is polar covalent, our dipole is going to be directed towards the chlorine, which is more electronegative. And here's hydrogen, oxygen. If we look at the difference between these two electronegativities, 1.4, polar covalent, with oxygen being the more electronegative. Now if you use your little delta positive, delta negative, delta positive, delta negative, that would be acceptable as well.